Okay, now we're going to talk about section 2.2, limits at infinity. And a lot of these we are going to do by looking at the graphs. So, looking at this, yes, a limit at infinity is essentially like an asymptote, often, and so sometimes they don't have asymptotes. So, investigating the graph of this, and where does it go? Well, we can think of it like this. We know that as we approach infinity, plus one doesn't matter. Sorry, grade schoolers, infinity plus one is still infinity for all practical purposes. This square root of x squared could be interpreted like, actually, it is the definition of absolute value of x. Okay. So my denominator is basically absolute value of x as I'm approaching infinity. The reason it's absolute value, when I square something, that makes it positive. When I square root a positive number, I get a positive. So no matter whether I put in a positive, like positive 5, I square it, I get 25, square root it, I get 5. Or negative 5, when I square negative 5, I also get positive 25. When I square root 25, I get 5. So when x is positive, so if x is greater than 0, this is just x over x, which is 1. If x is less than 0, oops, let's put my absolute value there. That's like saying it's negative x over x, or negative 1. So my limit at positive infinity of my actual function, that equals 1. My limit as x approaches negative infinity is equal to negative 1. Okay? That is example 1. Example 2, we're going to do finding this limit. And we can kind of logic our way through this, but it's 0. We can look at the graph or a table and see that it's getting closer and closer to 0. 7.8 e negative 4. I don't know how it got e negative 5 and then back to e negative 4. Something's wrong there. But once we start to get e negatives, that's like times 10 to the negative 5. That's getting very close to 0. We could also kind of logic our way into this. Sine is at its greatest 1, at its largest negative 1. X is going to infinity. 1 over infinity is always 1 over anything really large is approaching 0. Okay. And yes, I'm skipping writing that limit notation to make it a little quicker. So there's a lot of things where we can simply kind of logic it into, plug in an infinity, think about what happens. The graphs are very helpful. All these properties of limits still apply, whether they're at infinity or c a constant. So when I get down here and I see this limit here, I'll make it a little bigger and we'll work through it. Limit as x approaches infinity of 5x plus sine x over x. Well, I can split up my fraction to have this. and really ultimately do the limits separately. I'm not going to write the limit as x approaches infinity. The first one, 5x plus 5 is 5x over x is just 5x. And this one we just did in the last problem. That's 0. So what is my limit? 5. Hopefully that's pretty easy so far. We can also have limits. Sometimes limits go to infinity. And we'll start with the basic one that's not here, which this is 1 over x. I'm looking at my vertical asymptote. All the limits are simply the values except limit at infinity or negative infinity. They both go to 0. That's my horizontal asymptote both ways. But my limit as x approaches 0 from the left, I'm going to call this g of x, which is simply 1, that's just 1 over x, is negative infinity. My limit as x approaches 0 from the right of g of x, so I go from the right, I'm curving up towards, so here, as I go from the right, I'm curving up towards positive infinity. And my limit as x approaches 0, those don't agree, so it does not exist. My example here in 4 is 1 over x squared. And its graph looks like this. We can see that our right-hand limit and our left-hand limit both equal positive infinity. So this limit, since they are both the same, does exist, and it is positive infinity. So you can have a two-sided limit along a vertical asymptote. If they're both going the same way, that limit exists. If they're not, like in this example here, the limit does not exist, but the one-sided limits do. In a long vertical asymptotes, your limit, there's two options along a vertical asymptote. It's one of those two. You need to get it right, but those are the only two answers. Um, we can look at the tangent. If you remember from pre-calc, the tangent has all these asymptotes where the cosine of x equals 0 because tangent of x is equal to sine x over cosine x. I'm pretty sure I proved that in pre-calc. You can believe it for me. Where cosine equals 0 is the ones you can see on the graph here, negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2. There. So, if I'm looking at where does it equal 0 coming from the right side, well, coming from or where does it equal negative infinity? All of these coming from the right side are negative infinity. So this whole list could be true for values of A possible values of A. Now, when I come from the left side, it's never going to equal negative infinity for those values of A. Will always equal positive infinity. Again, I can look at it as I'm going at it from the right side. I'm having a hard time drawing straight with this thing right now. But I'm going from the right at my vertical asymptote here. And it goes to positive infinity. Well, we will often use these for what we call end behavior models. An end behavior model is simply a model that it's going to approach as I go towards its ends. End behavior being way out on the positive or negative x-axis. So here I've got two functions, and they're going to make a division out of this. So I've got f of x. Let's not cross it out. Let's underline it. I've got f of x and I've got g of x. And they've got f of x over g of x. And it works out to be this. And I think they give me the two functions here graphed. So I can functionally divide all of them. And we used a little horizontal asymptote trick, which was take the largest over the largest, which works out to be this. And you could use that in pre-calc because we've got all these, and we can do all these limits separately. 2 over x, 1 over x squared, 5 over 3x squared, 2 over x. As they approach positive and negative infinity, that is 1 minus 0 is its limit, plus 0 minus 0 plus 0. Oh, what a large, nice little limit of 1. So the right end behavior model for f and a left end behavior model is both 1 if you have an equal first term of a polynomial or an equal leading term. Well, sometimes we don't have equal leading terms. This one might be. So here we have our two functions, and the scan's a little light, in case you can't see it. F of x here is x plus e to the negative x. G of x equals x. So my limit as x approaches infinity, we'll get roughly the same thing. No, we won't. They're doing x over g. So I'm going to split this up, x over x plus e to the negative x over x. And I'm not going to keep writing the limit. As e to the negative x approaches infinity, e to the negative x has a graph that looks like this. And we can see that that is going to 0. So that's 0 over infinity. Well, 0 over infinity is definitely 0. So this is 1. But I'm going to get a different result if I do this for negative infinity. And I still have the x over x plus. And I can think of x plus x is still 1. But e to the negative x over x. And this is where it gets a little interesting. This isn't actually in their example. They did f over h when they did negative infinity. E to the negative x over x, well, e to the negative x is going to infinity. So is x. Which one's going to infinity faster? E to the x, the exponential, or x? E to the x is going much faster. So this is actually infinity. And you could look at the graph. They've got the graph here. Kind of. Let's put it into a graphing calculator and let's actually look at that graph. Because we're going to see that the e to the x And there's some ways later that you can prove it. We're not going to do that yet. We're going to focus on looking at hmm. I'm going to enter this x. And if we look at this, we could see that as I go to infinity, it was going to 1. Here, I'm actually going to negative infinity. Oh, I missed something when I wrote this up. So, so I had my x plus e to the negative x over x. And I'm looking at the limit as x approaches negative infinity. So x over x plus e to the negative x over x. And so that's 1. This goes to positive infinity. Remember that its graph looked like this. X goes to actually negative infinity. But I noticed that infinity over infinity isn't always infinity. Notice this is going to negative infinity. So now I've got 1 plus, because the e to the x grows much, much faster than the x, so divide e to the 1 million divided by a million does not cancel out to 1. E to the 1 million is probably numbers too large for me to say. I don't know how to say numbers that big. Dividing by a million's significant, but it's not that. But what's important here, infinity over negative infinity, is that I do keep that negative sign. Does adding 1 to infinity matter? No. So this limit here that we started with was negative infinity. Okay. And we can confirm that on the graph as this is going down towards negative infinity down here. Looking at that, and it just keeps going down and down and down. Just a couple more examples here. Finding an end behavior model. Again, this is the trick I taught you in pre-calc. Take the largest over the largest. 2x to the 5th over 3x squared. 2/3 x cubed. That is an approximate end behavior model. You can do synthetic division to get a more exact one, but usually this is good enough. This one, 2x cubed over 5x cubed. Well, my x cubes here are going to entirely cancel, and I just get 2/5. So that one's end behavior model is a horizontal asymptote. The first one's end behavior model is a cubic. So all that division, if I zoom out far enough, it's just going to look like a y equals 2/3 x cubed. Um, this one, 4x squared over 2x cubed. So that reduces to 2 over x. If I look at this limit, if I'm looking at the horizontal asymptote, I can do infinity or negative infinity. They're both going to be the same. 2 over x is going to look a lot like 1 over x. Its graph looks like this. And I know I told you guys this in pre-calc. Anytime there's an x left in the denominator after we simplify, it is 0. So yes, it does have a horizontal asymptote. It's a big fat 0. We're approaching the x-axis. And one final example. Using substitution. So here we have the limit as x approaches infinity of sine of 1 over x. Now I know 1 over x, if I'm talking about this limit, that's 0. So I can do this limit as x approaches 0. It's approaching 0 from the positive side. It's slightly larger than of sine of x. And sine of x happens to be 0. If I had done this with cosine of x, cosine of 1 over x, my thing is still 0, so I can still do that same substitution. The one-sided does matter sometimes, not in this case, and that is 1. Okay? So do not make the mistake of just going, well, that goes to 0, so the thing must go to 0. It did with sine, it does not with cosine. Okay? And that is section 2.2.